Okay, so last time we finished up on talking about the basic types of convergent boundaries. Now we need to go into a little bit more about the details of these divergent boundaries. Sorry, these convergent boundaries. The first one I want to talk about is the Oceanic Continental Crust, Continental Convergence. Right? In an ocean continental convergence, what happens here is you have oceanic crust coming in contact with a continental crust. That oceanic crust will come, because the oceanic crust is more dense, more mafic, right? It will go underneath the continental crust. And as it does, it brings volatiles with it, water. And that water will go down, therefore causing the melting temperature of the mantle to decline or to go down, causing magma to be generated. That magma will go back up through the crust, becoming more intermediate or felsic, and forming these stratovolcanoes, right? So these stratovolcanoes are characteristic of places, convergent boundaries around the world. And these areas also have really big earthquakes because as they go down, there's a lot of friction with that crust as it goes down, and therefore causes these big earthquakes there. We'll talk more about earthquakes in a little bit later, but the point comes is they're very large earthquakes that are associated with any kind of convergent boundary. Here's another example of a convergent boundary for here in North America. This one is what's causing Mount St. Helens, Mount Rainier, all these different volcanoes up and down the Cascades of North America. So this is what's happening is the Juan de Fuca plate, which is a convergent boundary, and you have the Pacific, what we call the Juan de Fuca rise, which is these guys right through here. Okay, these are the divergent boundaries. They're pushing apart the plate. The Juan de Fuca plate's going underneath North America here, and then causes the Cascades on the other side. So here's the mafic material going down beneath the felsic or more intermediate crust, continental crust, to form these intermediate and felsic volcanoes. Okay, so here's Mount St. Helens, great example of one of those stratovolcanoes that are formed. Okay, I think if I remember right, one of you guys are living in that area right now, or was from that area, or something like that. Okay. Then you have what we remember that we did this one last time when you have oceanic convergence. And you have both those crusts coming together. The colder and the older one, because it's thicker, is going to go down, and as it goes down, it's going to actually form a trench with it. Okay, and then the volatiles or the water is going to actually come back up, forming a volcanic arc. Before we call these continental arcs or volcanic arcs. Whereas these ones we call volcanic island arcs. Okay, and these still have stratovolcanoes. They're not as dangerous as these guys. Okay, but they have mafic or intermediate volcanics. Okay, so some cinder cones, maybe a shield cone here and there, but also stratocones. Okay, a good example of this might be Japan, Tonga, Fiji, some of those island nations of the South Pacific, right? Okay, so here you go. Here's some examples of that. Here's also the Aleutian Islands is a good example as well. As the Pacific plate goes underneath the North American plate, forming the Aleutian Islands all along the coast, forming these big stratovolcanoes. Same thing that's happening here as this plate goes down, forming the Marianas Trench, which is the deepest trench in the world, by the way, and forming a big chain of volcanoes right to the south of Japan and around Fiji and Tonga and the areas just north of New Zealand. Okay, and Samoa is near that area as well. It's part of that. Okay, the last one is continental convergence. Now notice in all of these ones before, all the other convergent boundaries, there's volcanics associated with it. However, with convergent boundaries that are continental, there is no convergence, and there is no volcanics. And the reason for this is because if you have to have some interaction with the asthenosphere, and you have to have melting. If you have two continents, they're both the same density pretty much. One stacks up on top of each other, forming the big mountain range and a plateau behind it. There's no decrease of pressure. There's no added volatiles, and there's no added heat anymore, and therefore volcanics dies out. So the volcanics can be there before it was a continental convergence, so that the old volcanoes, but they'll die out as they suture together. Okay. Now I've said that word suture on purpose because even if we have a suture for, like, say we had a big cut in our hand or something like that, we'd suture it back together or form together, right? Well, we also have this same process occurring. Where we have continental crust that can be sutured onto other parts of the crust. A good example of this today, that's happened today, is that India is slamming into Tibet, slamming into Eurasia to form the Himalayas and the Tibetan Plateau. This is also occurring where Italy was slamming into to form the, oh my gosh, not the Andes, I can't think of it. Anyways, the mountains north of Italy. I just lost my train of thought there. Alpha means the starts with an A as well. Anyways, doesn't matter right now. And so, actually, it's going to bug me. As soon as I paused, I remembered it. It's the Alps. Okay. So sorry about that. So as Italy slams into the coast here, it is forming the Alps through this area, right? Okay. And this is where Africa down below is actually running into Europe to form these features here. Okay. Okay, so those are some examples. Now this happened in the past as well. When these islands off the coast slam into the coast, they form other parts of the crust, or they get sutured onto the crust. That happened all over North America, especially in the western United States, where all of California, Alaska, all these are old islands that were off the coast that slammed into the coast. Now, I don't care if you understand what an accreted terrain is versus a suspect terrain, but the point is I want you to know what a terrain is, which is a region of geology that's different from the adjoining regions, and they're usually because there were old island arcs off the coast. Okay, they were formed because of an ocean-ocean convergence, then that continental crust that was formed now gets slammed into the coast to form part of that continental crust. Okay, so here's an example. Here's a trench here, an island arc, an inactive arc, the one that died out a long time ago, and then it keeps going in, slams into the coast, becoming part of the continent. Here's a portion of a microcontinent that also keeps coming in, gets slammed in to become part of the continent. Well, this happened in the eastern United States as well. This is what happened. We had what we call the Tectonic volcanic arc that was about 600 million years ago, and it was active, forming these big volcanoes off the coast. So here's a ocean-ocean convergence, forming this felsic kind of continental crust in these volcanic arcs. And as it keeps coming together closer and closer to, because this stuff over here was pushing on it, forming this, causing it to go closer and closer together until all of a sudden all this stuff broke off down here and then slammed into North America, okay, forming what we would consider just west of Charlotte today. Okay, although that rocks in the Piedmont is portions of those mountains. Okay, then you have Avalonia here, which is another microcontinent that was kind of the same thing, where you had a volcanic chain of islands. Okay, get slammed together and hit this region. That happened about 350 to 500 million years ago, and that one is what caused like Morro Mountain areas just east of Charlotte. Okay, another big island arc coming slamming in, and a lot of our neck of the woods as well, but a lot of it's been eroded away since. Okay, then you had Africa slam in. So this is an ocean-ocean, okay, convergence, ocean-ocean convergence again. Okay, then it slammed into North America, forming a continental convergence, and we call that the Alleghanian orogeny, where big, basically Appalachian mountains were formed, and then slowly over time got rifted apart, eroded away to form what we call the coastal plain, Piedmont, and the mountains of North Carolina today. And that's really how North Carolina got formed. It's this long process of slamming into these different island arcs into North America to form the rest of North Carolina. Because if you remember, all we had was the Blue Ridge initially, and then we had all this material start coming in, slamming into the coast over time. So this is a question that I wanted to remind yourself. What's the difference between a passive continental margin and an active continental margin? Now remember, a passive continental margin means that there is no subducting slab, which means there's not very many tectonics there, not very much volcanics, not very much many earthquakes. And so these are places where earthquakes happen. The questions here, earthquakes happen frequently at a passive margin, but not active ones. That's false. That's opposite, right? Why continental shelves occur at active margins, but not at passive ones? Once again, this is opposite. You have the continental shelves because all that sediment coming off the continent then gets pushed out on the shelf, forming this nice shallow sea right outside, right off the edge. And that's what's happening here in North Carolina. You have a big shallow sea going further out into the ocean. The crust is much thicker at a passive margin than in the interior of a continent. That's actually not true. It's actually thinner. But really what it comes down to here is the last one here. Passive margins are not plate boundaries, whereas active margins are. The active margins, or where plate boundaries occur, have active tectonics, active earthquakes, active volcanoes. So eastern United States is not a place where we have an active margin. It is a passive margin. The western United States, though, the whole western part of the western United States are active margins. Okay. The last type of plate boundary that we haven't talked about yet, sorry about that, a little itch there, is a transform plate boundary. And that's where the plates are moving side by side. Now remember, at divergent plate boundaries, you can get shield volcanoes, right? And any type of divergent boundaries, you're going to get volcanics. At convergent boundaries, you get volcanoes at anywhere where you have subduction, where you have the material going down because of that added volatiles. Continental convergence, you didn't get volcanoes. Well, guess what? At transform, you don't get volcanoes either. And the reason is once again, you have nothing that's going to cause it to actually melt. So no added heat, no added volatiles, no decompression. So therefore, you have a transform fault sliding past one another. Okay. The best examples of this is the San Andreas fault. You can also have them when one portion of a divergent plate boundary is moving faster than another portion. Therefore, you have a transform fault in between them. Okay. We call these fracture zones. So some features that you might find along a transform fault are valleys that are offset, like this one right here. You can see where this is an orange grove where all of a sudden the oranges actually are offset through here, okay, as you go through it. So you can form things like where there's bends, you might have actually a hill get formed because as it bends around, it will push on it. So like this one's going this direction, this one's going this direction. So you have these mountains being formed here. And that's really what's forming these mountains right here, right next to Los Angeles. This is the mountains that are formed right there where the Hollywood Hills are, where Beverly Hills is, right? Where the Hollywood sign is. Those are formed because of compressional hills caused by the bend in the San Andreas Fault. Now, if it was going the other direction, let's say it was going this way and this way, it's not, but if it was going this way and this way, you'd form valleys. And that happens in other places as well. If you look over here near San Francisco, you can have these valleys that form right here around San Francisco and to the north. And these are the pull apart valleys that you have there. Okay, so you have pull apart basins or compressional hills or mountains. So, this last question is, besides your divergent boundaries, your convergent boundaries, and your transform boundaries, there's one anomaly that we haven't talked about yet. And this is what we call hotspots. These occur when there's somewhere in the asthenosphere, it's hotter than usual. And then it's usually because there's more radioactive materials in that location for some reason. And these come and go with the changing of within the asthenosphere and the mantle. But the point comes here is these hotspots will get a lot hotter, causing the stuff above it to rise in just one central location. And as it does, you'll form volcanoes above it, like Yellowstone or Hawaii, are great examples of hotspots. Where Yellowstone is an example of what we call a continental hotspot, where the hotspot's coming up inside of a continent, where they're much more dangerous because they're going through continental crust. Or you have Hawaii, which is a oceanic hotspot that goes through the mafic ocean crust. Therefore, it's shield volcanoes and things like that. Okay. So, which of the following statements about hotspot track is correct? All the volcanoes making up the track have erupted roughly at the same time, and that is not true. We'll talk about that in just a second. The track is perpendicular to the movement of the plate is which the volcanoes which is moving. We'll talk about this in just a second as well. As a volcano actually burns through here, then it will form a volcano. As it moves, another volcano will be formed, another volcano will be formed. So it's actually going to be parallel with the actual direction in which the plate's going. Okay, hotspot tracks are parallel to deep ocean trenches. Actually, that's not true. They should be perpendicular. And the youngest volcano of the track occurs at one end of the track, so it occurs at the place where where the hotspot is, and the oldest stuff occurs as it goes away. Okay, we'll show you that in just a second. So here's this evidence of this hotspot. These are all the hotspots all over the world. There's